Well, hello, class, and happy Mother's Day to all the mothers out there that are watching this with your sons and daughters. I mean, invite your mom in to watch the Electromagnetic Field Theory Lecture. Don't do that to your poor mother. Today, what I wanted to talk about, I'm going to put together a couple lectures and then take the rest of the day off because it's supposed to be horrible this morning and freezing. 34 degrees this morning in May. I mean, it's May 10th and it was 34 degrees. You know, Charles Kuralt always thought that it wasn't global warming, it was global cooling, and that the ice age was coming back. And what he mentioned in it was that you could see the ice age coming back because we'll keep having snow further and further and further into the summer until the time that we're having snow off and on all through the year. And that, of course, builds up the glaciers over hundreds of thousands of years. But I don't think we have to worry too much about that because we'll all be dead before then. So on that cheery thought, what I want to do today is I want to look at, I'm going to do two things. I'm going to continue on with electrostatics, and we're going to expand out of point charges and multiple point charges so that we can get into other electric fields and figure out how things are working in there. And you're probably thinking, well, point charges, the next step past point charges would probably be, excuse me, line charges. Right, I'm having coffee and everything. Just had breakfast, so whatever. We'll see how it goes. So that's what we'll be moving on to, is line charges next. And with line charges, that sort of opens the door for us to look at high tension power transmission lines and how the electric field around those lines propagates. Right? And sometimes you have a 2-line system, sometimes you have a 3-line system. But we'll look at that next. But what I wanted to do to start out today was I wanted to look at the del operator, right? And every once in a while, you've probably noticed from the very beginning, I've been trying to point out some higher mathematics properties of a variety of different things, whether it's the coordinate systems, and get you guys up to speed on spherical, cylindrical, and Cartesian coordinate systems. That's one important thing, that it stretches outside of electromagnetic field theory. And this is too, and this is something that I'd like to show to you. As an example, I've always felt that a lot of times in electromagnetic field theory, you'd get very good mathematicians that then didn't realize that the students weren't really up to the same speed as them, and then they just lose most of the class. And I think that's the way a lot of professors really work. They don't realize that their primary focus is to make sure the students learn. They're just busy dumping it out there. So let's look at this. I want to teach you to look at the dot product, and really that's what we're going to be doing. We're going to be looking, I'm going to be discussing something where we've got the del operator working on some type of scalar field. Right? Scalar field could be anything, and I'll talk about that in just a second. So we're going to be working on some type of a scalar field here. And let's say right now I will just call that sigma. Right? There's no thing over sigma because the operator, the del operator, let's go back to the del operator and just write down the del operator in Cartesian coordinates. So that would be the derivative with respect to x, I hat, plus derivative with respect to y, j hat, plus the derivative with respect to z k hat, right? That's what the del operator is. And so if I'm going to use the del operator on a scalar field like I've got here, now let's just look at that. If I was to use that on the scalar field that I've got here, I'm really talking about the change with respect to x of sigma in the I hat direction plus the change in sigma with respect to y in the j hat, and then the change in sigma with respect to z in the k hat direction, right? So all I've done is I've just multiplied the del operator by the scalar field that we've got here. And you're probably saying to yourself, hey, what's that up there? Sigma equals x, y. Now, here's what I'm going to show you. This over here. I actually drew this up before I started the lecture, as you know, because you came to the lecture, and it was already sitting there, wasn't it? So I drew that up, and what that is that is a sheet, right? A sheet of material. Let's just say that. And let's say that I have doped that sheet of material. So here's what we're really looking at. We're looking at a very thin sheet of material, right? Very thin sheet of material. And I have used some type of doping process to enhance the conductivity of that sheet. And right down here, you'll see this is the lowest conductivity, and up here is the highest conductivity. Now you're probably saying, well, could I do that with anything? Could I have done it with, you say conductivity, but could I have done it with thickness? Could I have said that yeah, I've got a plate and the plate is getting thicker up here, right? So it starts off very thin here and then it gets very thick up here. So I could be talking about conductivity. I could be talking about thickness. I could be talking about mass, right? All of those are scalar quantities. They have no direction. So whatever I have here is a set of numbers that correspond to each of the various different x and y locations on this sheet, right? So what I've basically done is I've basically slotted the sheet out just like I've done here, and then I've calculated what the conductivity is. Now, like I say, conductivity, any characteristic, conductivity, thickness, mass, transparency, right? Maybe we've got something that's very transparent here, but not as transparent here because we've been blasting a sheet of plexiglass obliquely with UV rays for 6 days, right? Whatever it is, whatever quantity we're looking at over that sheet, right? Now, come on, get back here. Focus up. What in the world? I mean, I just, oh, there you go. Okay, good. I have taken the autofocus off. And so it still goes out every once in a while because, LIT is just the worst people in the world, technically. Oh, my God. Anyhow, let's get back to this because I want to teach you and I want to give you the tools to use so that in the future you can point this out to other people. It's like magic. What I'm going to show you is like magic, right? Okay. The first thing we have to do is we have to talk about, before I get into this, is we have to talk about unit vectors. All right, unit vectors. Now, I talked to you about that And we've talked about the unit vectors in the three different directions, the I hat vector, the J hat vector, the K hat vector. What do those three have in common? They're all 1 unit long, aren't they? Well, let's just take a vector. Let's just take any vector. Give me some numbers. Oh, that's right, you can't because you're not here. Well, I'm going to say it's 2I hat minus 3J hat plus 4K hat. How about that? Okay. Now, how do I find the unit vector of that vector in the direction of that vector, right? So I want a unit vector. So I want a vector that the total magnitude is going to be 1, right? So the total magnitude is going to be 1, but it has to be in the direction of A. Now, how do I do that? How do I get that unit vector? Well, if I wanted to get a unit vector and that's what you get, a little cap. See, a little cap means it's a unit vector, it's not a vector. And the way that we do that is we take the vector A and we divide it by the magnitude of the vector A, right? So let's find out what the magnitude of the vector A is. The magnitude of the vector A is going to be 2 squared plus 3 squared, so that's 4, plus 9, 13, plus 16, right? 13 plus 16 is 29, so it would be the square root of 29. Okay, I don't know what the square root of 29 is in the top off the top of my head, but I do now, and it is 5.385. All right, so 2 divided by 5.385 is 0.37, so 0.37 I hat. And then 3, well, minus, let's put the minus there. And then 3 divided by 5.385 is going to give me 0.557 J hat. And then 4 divided by 5.385 is 0.743 K hat. Does everyone see that? So that's what the unit vector would be. And you're probably thinking, well, how do I know that's a unit vector? Well, let's just see if that's right. Is the square root of 0.37 squared plus the square of 0.557 squared plus the square of 0.743 squared, taken all to the square root, does that actually give me 1? Let's just see. I'm just going to pop it in here for a second. 0.37 squared plus 0.557 squared plus 0.743 squared equals, taken to the square root, 1. Right? Does everyone see that? So yes, it is 1. Oh my God. Now what have I done to my poor studio? Okay, we're back. That's right, it is 1. And that means that it is a unit vector in the direction of the vector A. All right. Well, that's good. And what I'm getting to, though, is this identity that if I have, I should write it, yeah, I'll write it up here. If I have del times a thing, I'm just going to use this sigma. So if I have del dot sig or del times sigma dotted with dl, and then I'm going to put a cap over the top of that, right? Then that's going to give us the change of that variable in the direction of L, right? In the direction of L. And I want to go through that. I should have written that down here where I had a little more room, but you get the idea. And to get that DL with the cap on it, I've got to use the concept of unit vectors in the direction of in the direction of L, right? So we've got to do that. We've got to take DL. I mean, if you look at it, DL with the cap on top of it is really equal to DL divided by the magnitude of DL, right? So that's what we have to do. We have to figure out what the magnitude is, and then divide it by that, and that's what I've got to get DL. So that's what I wanted to start off with here. I've also realized that once again, I seem to have this phobia about never putting the timer on, but I know what I want to get through in the lecture, and it usually is one sheet, and that's about 30, 35 minutes, maybe 40 minutes sometimes, maybe 25 minutes other times. Now, let's get back to this, because this is such an interesting and powerful tool that you can use. Now let's look at this. Okay, so you can probably see from this grid right here and from this equation that I've got that at each of these various points on this thin slab of copper, right, I'm going to have different conductivities, and I've got those different conductivities because of some type of doping arrangement I've done to the thing or whatever, right? Let's not overly worry about that. Each one of these XY points, though, has a different value, right? How is it? It seems like they, anyway. So they all have different values, and in fact, the way that they are related is that the conductivity at each of these individual blocks that I've got here, that I've designed on top of the copper here, each of those is going to have this characteristic associated with it. All right. Well, if that's true, then let's apply the del operator to this. Let's get to this point, right? So if that's xy, we only have two things here. We only have, I've drawn the del operator out for a three-dimensional system. I'm using a two-dimensional example, though. So I'm using a two-dimensional example, so we don't really have to worry in this case about the k, right? So let's not worry about that. But let's take the derivative of this with respect to x. So the derivative of that with respect to x, in fact, let's just draw this down here, right? It's just a two-dimensional thing. So take the derivative with respect to x, and that would give me y I hat. And then we take the derivative with respect to y, and that gives me x j hat. I hope I haven't lost anybody. I'm just taking the partial derivative of that equation with respect to x, and then I'm taking it with respect to y, and I couldn't get a much, and you can basically see how it's laid out here as far as sigma equals xy, just for our little grid. Now, I've taken that, and so I've got this. And we could do the last one too, take the derivative of that with respect to z, and of course it's nothing, so it's 0. So this is what we've got. Now, let's look at a direction that we want to go through this. right? So the direction that we want to go through this, let's say that we want to go right through number 1 in the x direction. So we'll say that that would be 1I hat plus 0j hat, right? So basically what that is saying is that we're going in the x direction. We're just going in this direction, right along there. All right, right along the x direction. Let's dot those two together. First of all, what's the unit vector here? I think everybody can see that this is the unit vector, isn't it? In fact, if I've got that, I could write this as 1 I hat, couldn't I? I should really put, just a second. Let me just check one. Hi, I'm back again. And I decided to get rid of the D's in here and just make that L. The D is really already included inside the del operator. So let's make this L. And then this, of course, would become L with the little cap on top of it because it is only 1 in that direction. Now, let's look at a certain point here. Let's choose a point. Let me just choose this point right here. Now, what would that point be? That would be 3x, or x equals 3, y equals 1. X equals 3, y equals, actually I shouldn't do that because that is a 3 and x equals 3, well, we can't do anything else. Now, let's come up here and do this one then. No. We want to go along here. So if I dot I'm going to dot the two of these together. Right. So let's do that. Let's do that first because we know that this is the unit vector. Now, what if instead of going along here, right, I'm going to look at the gradient. This is going to tell me how much this drops each point that I go to. So let's do this one first. So if I have this, let's just pick a point. It doesn't matter which point we really pick on here. Pick this point right here. So 4, 1. Anyway, first let's do this. So I've got del times sigma, right, dotted with the unit vector in that direction. In this direction, this would be the 1I plus 0j. That's the direction I want to find the gradient in. And that's the gradient. By gradient, I really mean slope of the line. I think everybody can see that it goes up 1 each time, doesn't it? Wouldn't that be what the gradient is? All along that line, it's going to go up 1. So let's see if that's right. Well, we've got y times I hat plus x times j hat. And that's going to be dotted with 1 I hat plus 0 j hat. Now, usually I wouldn't put the 0 j hat in there, but what the hell. So I've got x times 0, well, that's 0, and I've got y times 1. So really what this tells me is that the gradient along that line is going to be y. Right? So let's look. Let's just put a point in here. Let's put this point in here, right? Because that's going to be, and this is going to be our gradient. I'm going to put a disclaimer in here. At that point. You got it? That's the gradient at that point. And so you're probably thinking, whoa, what does that mean? The slope of the, yeah. Well, what if I had a graph like this? right? And I had something that looked like that. Now, what is the slope of that line at any one individual? It's not the same, is it? Because look at the slope of the line down here. Slope of the line down there goes like that, right? Whereas the slope of the line over here goes like this. And that's really what we mean by the gradient, isn't it? We mean the gradient or the slope. So along here, along this line, we can see that the slope is y. So at any point along that line, let's take that first point. Let's take point 1, 1. Let's do that one. So at point 1, 1, the gradient at that point going in this direction, is going to be y. So it's going to be 1 at that point. Let's go to another point. Let's go to the point 2, 1. What is my slope of the line going to be there? Well, let's put it into the equation. The equation says that the slope is going to be y. So it's 1. Does everyone see that? It doesn't matter which of the points I put in here along this direction, I'm always going to get 1. From here to here, it's 1. From here to here, it's 1. From here to here, the slope is 1. From here to here, the slope is 1. Can everybody see that? It doesn't matter what I put in there. Now let's put another directional vector in there. Let's put this directional vector in there, shall we? So now we're going to I'm going to cut this off for a second, right? Because that was the first one. That's at that point. Now let's do the second one. So now I've got del times the conductivity at that point, and we know that that equals y I hat plus x j hat. And then what we want to do is we want to multiply that by, and let's do this one now. Now we're going in the y direction, so this is going to be 0 I hat plus 1 j hat, right? Because we're going in this direction now. I think everybody can see that it's going to turn out the same. Well, let's dot those together. So if I have del times sigma dotted with L with a little cap on top of it, so it's the unit vector of that L in that direction. I don't know. Maybe it's better. I'm going to double check it. Maybe it's reverted to autofocus or something. I don't know. But it seems better now. Anyway, let's go back to this. So if I have y times I times 0, well, that's 0. And if I have xj times 1, that's going to give me x. So in this direction, if I put any number in there, I can find the slope or the gradient, right? That's the gradient in that direction. I know you're thinking, how powerful is this? How incredibly powerful is this tool that Professor Grinquist is giving us right now? That's right. So it's x. So any point that I put in there in that direction, the slope between that and the next one is going to be x. So let's put this point in. That would be 1, 3. So if I put the point 1, 3 in there, the gradient from 1, 3 to 1, 4 and from 1, 2 to 1, 3 is going to be 1. Does everyone see that? You're probably saying, well, oh, no, of course, that just makes sense. We can see that it's 1. Why don't you do a slightly harder one where, it's not 1 all the time? I'm going to do that. I'm going to do, for the last one, I want to do this. And what would that be? What would the unit vector of that L be? Well, L is going to be 1 I hat plus 1 j hat, isn't it? That's the direction we're going now. 1i plus 1j. Now, let's dot that with the del operator times the conductance. And what we get when we dot del sigma with L. Now you probably say, hey, that's not a unit vector. Hey, that's not a unit vector, Professor Granquist. That's right, that is not a unit vector. Because we have to take that unit vector and we have to divide that unit vector by its magnitude, right? Which is the square root of 2. So the unit vector is going to be 1 over the square root of 2i hat plus 1 over the square root of 2j hat. Right? Everybody see that? Everyone see where I got the square root of 2 from? That's just 1 squared plus 1 squared gives me 2. The square root of 2 is the square root of 2. So that's how I got 1 over the square root of 2. So let's do that now. Let's dot those together. So this would be y over the square root of 2i hat plus x over the square root of 2. Oh, wait, what am I doing? I'm dotting these. Oh, my God. Up here, it really didn't make any difference. I dotted them together. And of course, you know, it's early and it's Mother's Day. So no, I got that right. I did everything right up to here. The only thing, well, good. I'm not as crazy as I thought I was. Oh, I love it when I pick up things like that. But yes, the gradient was x there. I don't have any, things over it, and it's a scalar. Right? So the dot product, in fact, this is a good opportunity to bring it back to the dot product is always a scalar. The dot product is always a scalar, so I dotted those two together. And I dot these two together too, and this is what it's going to be. I don't know why I put that I. Okay, so here we go. So the slope along this line is going to be y over the square root of 2 plus x over the square root of 2. Right? Well, let's do that for certain different. And I think that everybody can see that this is sort of like this, although it's going up the other way. So if I just drew this down here in this corner, if I'm going 1, 4, 9, 16, 25, it's not going up linearly, is it? It's going up like that. And so if it is going up like that, then my slope or my gradient is going to be changing all the time. So now the actual choice of the point that I'm going to be putting in there is going to change the gradient, right? Because as you can see, the slope starts horizontally but keeps going up higher and higher and higher. And so it is going to change. And so that's why we need the point. So let's look. I want to look at several points along this line. So let's look at this point from 1 to 2. So let's just put 1 in there. So if I look at that point right there, what's the gradient at that point 1, 1? So that would be 1 over the square root of 2 plus 1 over the square root of 2. And that would be 2 over the square root of 2. I'm going to put at 1, 1. Right? That's the first in our series. That's right here. So 2 over the square root of 2. 2 over the square root of 2, isn't that the same as 1 over the square root of 2? Because isn't that square root of 2 squared, and that's the square root of 2, so the one of those cancels out, and so that would just be the square root of 2. Oh, did I say over? No, I meant the square root of 2. So I'm just taking that out of there, and that would be the square root of 2. So our slope at 1, 1 is going to be 1.414. Right? Does everyone see that? I hope everybody sees that. What is going to be my slope at, let's go to the next one. Let's go at 2, 2. My slope at 2, 2 is going to be 2 over the square root of 2 plus 2 over the square root of 2. Right? So that's 4 over the square root of 2. Right? Or 2.88 is actually what it's going to come to, I'm sure. I just want to 2.82. Right? So you can see that right here I've got a certain slope, and then up there I've got a slope that's twice as great as that. Let's go to 3, 3 and see how that works out. So at 3, 3, the slope of my line is going to be 3 over the square root, or 6 over the square root of 2. Right? So 6, that gives me 4.24. It's really 3 times the square root of 2, but that's fine. Anyway, now I think everybody can see. I don't know if I have to keep going along here, going all the way through. What if we tried a different one? Like this is 1, 1. Well, what if we tried one that was 1, 2, right? In fact, I think that would be up here. Well, you know, I'm going to leave that up to you. It doesn't matter which way you go through here with the direction, right? But you have to come up with the directional line that you want to find the gradient on. And just like you can see, when I use this line, it's 1, 1, 1. When I use this, it's 1, 1, 1. But when I use this line here, which would be a 1 and a 1 direction, 1, 1 direction, if we went 1, 2, it would be up like this. Oh, wait a second. 1, 2, 1, 1 is that way. Yeah, it'd be up 1. Yeah, it'd be this way. So you could do it other ways too. It's just a powerful. It shows you a gradient. If you have some type of field like this, right? And this is related to X and Y, of course. But if you have some type of field like that, you can very quickly find the gradient in any direction, up or downhill, immediately, just by using your directional unit vector and the del operator across the scalar field. All right. I think as you look into this and you start to understand, this really is a valuable tool for looking at gradients, isn't it? That's right. And I'll throw some more in there as we continue to work through what I would consider more of the bland stuff, and that's really electric fields around high tension transmission lines. It's interesting too, and I love that too. But I just like to point this out, show you the higher order mathematics. You probably say, well, I'm never going to use that. No, not true. If you go into graduate work, I use calculus every day. I use things like gradient every day in my personal life. And I don't really like to say this, but John Wayne had a saying, and he said, life is really hard. Life is really hard, but it's a lot harder for stupid people. Which is right, and we should feel sorry for people that maybe don't have the intellectual capabilities that we have. But by knowing more, by understanding more of the mathematics, is a tool that lets us make our life better, lets us be more capable, so that we can help our friends, family, and society as a whole live a better life. Okay? All right, we're going to end it there. I'm going to do another one on what's probably very boring, but a derivation of electric fields around high tension transmission lines after this. No, 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 no. Okay. No, I thought I had paused the recording, but I hadn't, I guess. I don't know. I'm hoping I didn't.